Assalamu alaikum. This is the third video of the second chapter. So far we have discussed different types of topologies, given by the researchers, basically to handle the stiff DC fault current. So till now we have discussed different types of topologies. So now we are going to study another type of topology, that is 5-level cross-connected submodules. Basically, what the researchers are trying to do, they are trying to they are basically trying to insert these submodules capacitors whenever the fault occurs, and they want to basically uh, bypass the switches. They are not taking help from the switches, rather they are interested to insert the submodule voltage so that the the system basically from the AC side cannot supply power, cannot supply current to the fault side. So this is basically the idea what the researchers are trying to do. They are trying to uh, insert these submodule capacitors whenever the fault occurs in the system. So the same is happening in the 5-level cox connected submodule topology. We are basically getting 2V, V0, minus V, minus 2V. We are getting these 5 voltages basically using 5-level cross connected submodules, where V is the output voltage of the submodule capacitor. And what the author suggests, that it says that you can basically, if you are using 25% of the submodules, uh, they can be 5-level cross connected submodules, and the rest of the other submodule bridges can be H bridge. Now these 25% of the submodules out of 100% can be used to insert the negative voltage, and thereby the converter be able to block the fault currents. So this is a typical 5-level cross connected submodule topology. Here you can see these are basically two half bridges. These are two half bridges, and they are cross connected by these two switches and two diodes, D5, S5, D6 and S6. Similarly, you can see that if the fault has occurred, now the switches will be opened. And now what will happen, that if the current is positive, so the positive current will flow through this diode D1, and it will come here from this capacitor, and it will follow this path through this diode D5. It will come here. This capacitor will also be inserted, and then from D4 it will go out of the phase. So in this case you can see that basically both of the two capacitors are inserted, and they are able to block the fault current. So, and similarly, if the fault current is negative, so what will happen then, the current will flow into this submodule from this D3. It will come here, this capacitor will be inserted, and following this path D6 through D6, this capacitor will be inserted, and from this following from D2, so this is out of the current will be out from the submodule. So in this case you can see that whether the current is positive or negative, basically the submodule capacitors are inserted into the what you can call into the arm or into the phase, so that they will be able to block the fault currents. So this is basically a 5-level cross-connected submodule topology, and according to the authors, 25% of the submodule you can use as a 5-level cross-connected, and other submodules you can use as a half bridge. and the main advantage is that it can provide you negative voltages, and thereby you can control basically the fault current. Obviously, why the authors have suggested 25% of these, because you can see the complexity is basically increased by connecting these two half bridges via these two switches and two diodes. So we don't want to increase the complexity of the circuit, rather we want to uh, we want to we want to basically uh, control the fault currents. We want to control the fault currents. We don't want converter to lose its control over the circuit, over the different parameters. So this is basically a 5-level cross connected submodule. Now the next topology that we are going to discuss is just a simplification of 5-level cross connected submodule. So in this topology you can see that here D6, in this point basically we have removed the switch S6. Okay, so this is same as 5-level cross connected submodule, but the difference is that we have removed this switch S5. Now same negative voltage can be used to block the fault currents, right, in 3-level cross connected submodule. Now let's say if the fault has occurred and all the switches are open, what will happen? If the current is positive current will flow through from this D1. It will come here through this capacitor, taking path from D5. It will insert this capacitor. So this capacitor is inserted and this capacitor is also inserted, and it will flow from D4. It will on to this. Now if the current is negative, it will flow into this submodule. Following from D3, this capacitor is inserted. Flowing from D6, this capacitor is also inserted, and following from D2, it will be out of this submodule. So this is again a simplification, just a simplification of 5-level cross connected submodule. Now the next topology that we are going to discuss is basically a double submodule topology. Now this topology basically can be used. This topology can be used to connect two capacitors in series, in parallel, or equally bypass both capacitors. This is the beauty of this topology. Now what the research says, that it says that it basically says that elimination of low frequency components results in reduction of 18% peak to peak voltage ripple. Okay, and proposed submodule reduced voltage ripple without increasing the switching frequency. Yes, this is the big advantage of double submodule topology, that if we are increasing, we don't want to increase this, we are not supposed to increase the switching frequency, and our submodule ripple voltage has reduced without increasing the switching frequency. Hence, for giving switching frequency, size, weight, and cost of the submodule capacitor can be reduced. This is the big advantage of double submodule topology, that for the same frequency, size, weight, and cost of the submodule capacitor can be reduced. Okay, this is the typical topology, double submodule topology. Here what is happening, these are two, this is a half bridge topology, and this is just the addition of two diodes and two switches, and these are connected from this point. So what will happen, let's say this switch is on, this switch is on, and the capacitor is inserted, and if the switch is on, so the current will flow from here, and if the switch is also on, the capacitor current will flow from here. Okay, so this is a typical double submodule topology. So the next topology is semi-full bridge submodule topology. But there is a slight difference between double submodule topology and semi-full bridge submodule topology. What is that? It says that replacing two diodes in clamping double submodule active switches resulted in semi-full bridge submodule topology with two positive voltage levels and one negative voltage level. And the main benefit is that higher modulation index can be possible at lower cost compared to full bridge submodule topology, and energy variation can also be reduced and minimized. Where the maximum allowable modulation index is basically 1.41, and semi-full bridge with two capacitors can be connected in series, parallel, and the capacitors can be bypassed. Okay. So the research says that the semi-full bridge topology can be compared with the full bridge and half bridge topology. Semi-full bridge topology used switches, and these are S3 and S5, and they are always conducting in parallel. So the combined device rating in semi-full bridge submodule topology are basically 50% higher than half bridge and 25% lower than full bridge. So it lies in between half bridge and full bridge topology. Although series and parallel connection is an advantage of the semi-full bridge submodule topology, yet it leads to create a certain problems, such as when capacitors are connected in parallel, and if their voltages are different, so this creates a spike current and energy is lost in that process, in that particular time. And the research says that difference of 10% in a capacitor values and an increase of 2% in capacitor voltage during the time when they were connected in series would result in 0.01% of energy supplied during the series connection being lost when the capacitors are connected in parallel. So if they are connected in series and we are basically now connecting them in parallel, so 0.01% of the total submodule energy will be lost in that. Now as long as the voltage difference is within few percent, it is not a major issue that we are connecting the capacitors in parallel. This is not a big issue. Now using the negative voltage levels and submodules connection in parallel, it is possible to reduce the voltage ripple by 59%. This is the big advantage of semi full bridge topology, that you can basically reduce the voltage ripple by 59%, and no other topology can provide this reduction. There isn't any other topology that can provide us basically a reduction of 59% ripple voltage. So this is the topology. You can see here basically what is happening, that two topologies are basically connected via this diode and this switch S4. So this is a typical semi full bridge submodule topology. Okay, now in the past, what was happening with the development of semiconductor devices? Now, initially, these devices uh, were supposed to be was supposed to have a high power rating and a high switching speeds because they were used in motor drives and electric traction, etc. But in MMC, if we see in MMC, the phenomena is different, is very different as that has happened in the past. And what is that? We require a very low switching frequency. We require a very low switching frequency, and our concern is that the voltage drop must be very low whenever the switch turns on. Now, too much efforts are basically made to increase the switching speed, but too little efforts is spent on achieving minimum conduction losses. Minimum conduction losses is basically uh, are the most important in MMC. We don't want the conduction losses to be very high because our switching frequency is very low, and we are not interested in higher switching frequencies. So the slow switching devices with higher voltages have two advantages. Low relative onset voltage can be obtained, number one, and number two, using these devices with a very high voltage ratings, number of submodules, cost and complexity can be reduced. Now, if our devices can withstand high voltages and they have a relative lower on-state voltage, the benefit of getting these two advantages, basically these two features, basically are to reduce the number of submodules since our switches can withstand high voltages, and since they are having a low on state voltage drop, our losses can be reduced. So these are basically the two devices, these are the two these are the two attributes, these are the two features that we want in our semiconductor devices that are basically used in modular multi-level converter. Now we are going to study basically what are the soft switching submodules. What are the soft switching submodules? We are going to study this. Okay. So as I discussed earlier, the semiconductor devices are characterized in the past by higher voltage handling capability and higher switching frequency, but in MMC the scenario is very different. We need a very low switching frequency and a low on-state voltage drop. What the research says that IGBT has higher losses than IGCT. IGCT is insulated gate commutated thyristor. Moreover, the plasma distribution in IGCT yields to lower onset voltage drop than IGBT. So because of this feature, because of this plasma distribution, IGCT is having a lower on-state voltage than IGBT. So that is why the losses in IGBT are higher as compared to IGCT. But thyristor based switching on high voltages causes losses. So the solution to this problem is basically using soft switching submodules. What are these? To achieve soft switching, we have to introduce the capacitors and inductors to the commutation circuit. Now, soft switching devices with high voltage handling capability have two advantages. Number one, low relative on-state voltage can be obtained. Number two, number of submodules can be reduced by using high voltage rating devices. So this is a soft switching submodule with two basically capacitors CS and two main capacitors C main, and this is an inductor LA. This is switch S3, and this part resembles to half bridge submodule, but here the capacitor is basically broken into two. So a popular soft switching circuit topology for Lex-based converter is auxiliary resonant commutative pole, ARCP. This is an ARCP where S1 and S2 with snubber capacitance CS is basically snubber capacitance, and S3 is a bidirectional switch with LA inductor LA, and main capacitors are basically divided into two main capacitors divided into two. This circuit becomes complex, and additional cost is there because we are dividing two capacitors, this switch S3 and this inductor LA. So complexity as well as the cost of this circuit is increased, but a cheaper thyristor are used instead of IGBTs, and the number of submodules are also decreased. If we compare this complexity and the number of additional devices with IGBT, so we are using thyristor instead of IGBT, and because of the high voltage handling capability of these devices, the number of submodules can be reduced. Moreover, the losses of ARCP are 45% less than those of IGBT submodules. Now this is the big advantage of that. So we can conclude that if we are using soft switching submodules, the complexity of the circuit is increased, the number of devices and the cost is increased, but compared to using IGBT in our circuit, the number of submodules as well as losses are basically decreased using soft switching submodules. Now we are going to study that what are the basically requirements of the circuit parameters. What are the different things that we need to decide before going to practically implement modular multi-level converter. So the design process starts from the requirement of the power and the voltage ratings. It is not a straightforward decision that I need these number of submodules and I need these switches and I need the value of the capacitance is this. So this is not a very straightforward process. It needs certain investigation. So yes, required power and voltage ratings, initial values of the number of submodules, average voltage per submodule, submodule capacitance, inductance, and using all these initial values, various calculations and simulation are performed to fine-tune the final choice of the main circuit. Main input data. Now main input data is basically a certain amount of power that needs to be transferred, and for that we use transmission lines. So the transmission project starts from the need of certain amount of power to be transmitted. We have different voltages, we have different high voltages available, 80 kV, 150, 300 and 600 depending upon the distance between the sending and receiving end, and in DC side average voltage current are known, but in AC side reactive power are also to be specified. Yes, this is the thing. So the main input data we have to first of all select, and first of all we have to analyze what is the amount of power that we are supposed to transmit and what is the distance. So depending upon the distance we will select the number of voltages, and these number of voltages basically are very important to determine, because it is the voltage it is the voltage in the power lines. Because of that we decide the number of insulators, we decide the basically conductor, and there are different parameters that are supposed to be decided according to the voltage of the transmission line. Now the second choice is the semiconductor devices. Now, owing to the low switching frequency, devices with low voltage drops and high voltage handling capability are preferred in modular multi-level converter. And the current of these devices are chosen on two requirements. Number one, the normal operation current. The normal operation at rated current IN is basically IDN by 3 plus ISN by 2, where IDN is the rated DC side current and ISN is the peak AC side current. And we know that both AC and DC current are present in the converter whenever the current is in operation. Number two, choice also depends upon the DC side short circuit handling capability of the submodule. This is what we have been discussing since in the second video and in this video also. DC side short circuit handling capability. Now either diodes and inductor are rated to handle far current, or bypassing thyristor can be used. We have discussed this in the earlier slides. Choice of the number of submodule. This is also the main part of the submodule MMC designing. Now, choice of the number of submodule is not a straightforward decision. It needs certain investigation, such as at this stage we don't know that what is the submodule capacitance, right? And we know if we are using a low value capacitance, if the capacitance is very low, it will definitely lead to high voltage ripple, and this would increase the minimum number of submodules to produce the AC voltage. So the higher value of the capacitance means the higher cost. Now there is basically a trade-off. If the value of the capacitance is too low, that means we are definitely going to get a high voltage ripple. The voltage ripple will be very high, but if the capacitance is very high, the cost of the converter will be very high. So there is a trade-off between a voltage ripple and a cost of the converter. So a value is selected in a way that the cost is minimum as well as the voltage ripple is low, is reduced. So the design process includes the finding the value of the average sum capacitor voltage per amp. We have to decide this, what is the average voltage, right? And we have to decide basically what is the average submodule capacitor voltage, and we have to decide the number of redundant submodules. So let us see that how we can basically find this sum of capacitor voltage per arm. Now generally we know that if we sum up the submodule capacitor voltages in the upper or in the lower arm, we will definitely get the DC pole to pole voltage. But If the current rating of the semiconductor devices is not sufficient, then higher values of average sum capacitor voltage can be chosen, which is possible in case of modulation index greater than 1 and only be realized if the submodules can insert negative voltage. Now, what does it mean? It means that this is generally happens that the sum of the capacitor voltage is equals to the DC side voltage. But if the current rating of the semiconductor device is not sufficient, means if the semiconductor devices cannot withstand this current, then we have to increase the voltage in order to decrease the current so that our semiconductor devices can run efficiently and can withstand that current, the flow of current. So in order to compensate, in order to decrease basically the current, we have to increase the voltage. And how we can do that? In order to increase the voltage, we have to use, or we have to increase the modulation index beyond 1. And this is only possible whenever the submodules can insert negative voltage, right? So the second parameter we have is average submodule voltage, voltage of each submodule, and it can be selected considering the following parameters. Number 1, the ripple voltage. What is the ripple voltage? Yes, over voltage due to stray inductance of the submodule when switching maximum current, right? Maximum voltage of submodule during AC side fault and maximum submodule voltage during DC side fault. We have to select both of these. So these are the 4 parameters onto which the average arm voltage of each submodule is selected. Okay, so the third point is the number of redundant submodules. And number of submodules can be selected on the basis of previous data that n is equal to the sum of the capacitor voltages per arm divided by the voltage of each submodule, and it depends upon AC and DC side faults. And this point must be noted that single phase AC side fault makes the submodule voltage 1.3 times the VDCN, and in case of H bridge, but in case of full bridge it becomes 1.9 times the VDC, where VDCN is the voltage of the submodule. So the next parameter is choice of the capacitance. How we can basically select the size of the capacitor, how much charge, how much the value of the capacitor is in farad. So it must be chosen carefully. We know that high value of capacitor increases the cost and the low value of the capacitor increases the ripple. According to literature, the capacitance must be selected so that the overall sum of the submodules stored energy is 30 to 40 kilojoule per MVA. And the final value of the capacitance is chosen by means of an optimization where cost of the submodules is compared with the cost of the semiconductor devices. Choice of the arm inductance. Now normally dry type air core inductors are used, and inductor size can be chosen in 3 ways. That how basically short circuits are handled. Submodules with bypass thyristor or additional diodes to handle the fault current, where the inductor is used to filter high frequency component in the circulating current and enable smooth circulating current control. Normally the inductance site is 0.05 per unit. And if the thyristors and diodes are not used, then the inductor have to protect the anti-parallel diodes from the fault current till the circuit breaker opens. The value of the inductor is chosen normally between 0.1 and 0.15 per unit. And the number third is option is to increase the average sum capacitor voltage of the arm beyond to pole voltage to increase the current capability on the AC and to minimize the losses. And the choice of induction is not straightforwardly selected. Now this is the beauty of the modular multi-level converter, that whenever the any submodule fails, there is present a submodule that takes place of the faulty submodule, and that feature is basically called as redundancy. And we have to handle these redundant submodules. So we will discuss in the next video that how basically the redundant submodules are handled